I'm going to run a chi-square analysis for you using Excel, and this is the table I'm working with. Let me go back and show you. Let me actually set this up for you. All right, so the chi-square is an analysis that compares the observed distribution to a distribution expected by chance alone. And when I'm talking about a distribution, I'm talking about a cross-tabulation table where I have two variables. Each variable is discrete in nature, discrete categorical in nature. Generally, we deal with 2x2 tables where each variable has two levels. For instance, I could look at male versus female on whether one exercises 3 times a week, 30 minutes per day, yes or no. So it's two levels for each of the two variables. If we multiply those together, 2 times 2 equals 4, so there'd be 4 different cells in which we would drop data. The observed distribution is actually what we would find if we were to collect data from individuals and assign them to the appropriate cell. Like, for instance, if it's a male that exercises versus a female that exercises, each one would fit into their appropriate cell. The expected distribution is the distribution that would occur at random by chance alone, like if I took people and dropped them at random into those 4 different cells. Now let's take a look at this equation and then we'll go over an example that's similar to what I just discussed. The chi-square equation is, well, it's written with this Greek letter chi and it's squared, so that's why it's called chi-squared, not chi squared. Some people read this wrong as chi squared. It's a sum. Now, so you're summing across all the different cells. In the example I gave you, there were 4 different cells. We sum, so this sigma is the symbol for sum, and we're summing this quotient here. So it's the frequency observed, and let I equal 1 to the number of cells. If there's 4 cells, I can range from 1 to 4. So the observed frequency, FOI, is observed frequency minus the expected frequency. So we're looking for the difference. We're squaring that and dividing it by the expected frequency. To calculate the expected frequency, we use this equation. It's the row total. Let me add that parenthesis there. The row total times the column total divided by the grand total. And if you're interested in where that comes from, the values in each of the cells, and here's an example, just a second, I'll discuss it in a moment, but the values in cells are, basically these are considered successes. Like, I'm trying to find how many individuals have less than a high school degree and are also regular exercising. Success, I have 52 successes. Anybody that does not fall into that cell, that means there's 1, 2, 3, 4, 5 other cells it could fall into, is considered a failure in statistical or in probability terms. In probability terms, we generally like to discuss whatever it is we're looking for as a success, not qualitatively, just in our language, success, and then whatever we're not looking for as a failure. So these are the only 2 possible options in a sample space that has only 2 possible events, success and failure. So we can find out what the probability of success is by dividing the number of individuals in this cell by the grand total of all individuals. In this case, there were 431 individuals, 52 of whom fell into this specific cell. So 52 divided by 431 is our probability of success. Since these are complements, the success and failure, there's only 2 possibilities, and one thing we know about probabilities, they always have to add up to 1 within a sample space when we talk about all possible events, right? All possible events in the sample space, mutually exclusive events means they cannot occur together. It would be 1 minus the probability of success, so probability of failure would be 1 minus the probability of success. Anyway, the distribution of the number of successes is a binomial distribution, where each of these individuals represents what we call a Bernoulli trial, where it's a yes or no. Are you in this cell or are you not in that cell? There were actually, in this case, there were 431 Bernoulli trials. Each individual is independent of the other individual. So that what happens to one doesn't affect what happens to the other. So when we have this many Bernoulli trials, we have what's called a binomial distribution. A binomial distribution is the probability of each of these number of successes up to 431, right? The expected value for a binomial distribution is n times p, where n is the total number, or total sample size in this case, it's 431, and P is the probability of being in each one of these cells. So we derive this equation here by just using N times P. So here's the N is the total, and the probability of being in each one of these successes, this is a joint probability. So for instance, the probability of being in this specific cell here, you have to be both less than high school degree, so this 144 divided by 431, and is this universal notation for multiplication in probabilities. You also have to be a regular exercise, and the probability of regular exercising is 152 divided by 431. So this is basically how we derive this equation, and you'll notice since there's a total, there's 3 totals, 2 in the denominator and 1 in the numerator, we can cross out one of these bad boys here, and we get row total times column total divided by the grand total, and that's how we derive that equation. I don't know if you care about that or not, but I just like to do that. So let's look at this study here. We want to examine whether education level is related to having regular exercise, defined by 30 minutes 3 times per week among adults, and we want to know if they're significantly related. This is an ideal question for a chi-square. In this case, we have 3 rows, 1, 2, 3 rows, and 2 columns. Yes, so we have 3 rows and 2 columns. This will give us a total of 3 times 2 is 6 cells, right? By the way, when we, and I'm just going to show you how to do the chi-square, but when we do this analysis, you also have to determine whether we have statistical significance or not. The way you would do that is by finding a chi-square table, or if you can just look online and provide your degrees of freedom. In this case, I'm not going to cover all that, so I'll just tell you that the degrees of freedom is rows minus 1 times columns minus 1. So there's 3 rows, 3 minus 1 is 2, 2 columns, 2 minus 1 is 1, so there's 2 degrees of freedom here. And we compare it to a critical value, and since I just did this, the critical value here is 5.99. A chi-square, you'd have to look this up at a chi-square table. So that's just for your knowledge. I'm here to show you how to do this on Excel, though. So what I did is I copied and pasted that table into Excel. So I have the observed values. There's 52 in this cell, 92 here, 44 here. If we can label these cells whatever we want. You can do generally you'd use row followed by column. So this cell would be in row 1 and column 1. So you call it cell 1, 1. I'm just going to, just for sake of simplicity and for well, actually, you know, I'll do that anyway. What the heck? I'll put a 1 here. So that's frequency for cell 1, 1, cell 2, 1, cell... No, let's do this. Cell 1, 2. So I'm going to make this official. 2, 1. Make it easier for you to follow. 2, 2. 3, 1, 3, 2. There you go. All right, so now we're all set. So we have the equation, right? We have the equation. So I'm going to copy that equation. See if I can copy it in here. And I'll paste it in Excel. There you go. As long as you can see it, that's what counts. If I can highlight it, it would be awesome, right? There you go. And then I'll take the other equation as well and put that in here. I kind of like doing this in real time with you all so that you can see how I function, and you can like get mad at me if I do something wrong. There you go. And do this. There you go. So we're all set. All right. So we have the observed values, right? We need the expected values. So let's calculate the expected value. The equation is row total times column total divided by grand total. When I want to write an equation in Excel, I start by hitting equal. Now I can write the equation either in this cell or up here. Sometimes I prefer up here. So I need row total. So if this is for cell 1, 1. So this is this cell right here, because this is row 1, column 1, it's 52. So the row total is 144. So, and I also want to do this in parentheses just to separate it from the denominator. I'll highlight the cell, right? Cell E8. I'll multiply it. The universal symbol for multiplication is your asterisk. And I'll multiply it by the column total, which is 152. I'll close those parentheses. And use a slash to indicate division. I divide it by, well, I'm going to use, I'll just do 430. I'll just put this in here. There's a reason I was hesitating there, but sometimes it's wise to write the value down if it's going to be constant, because 431 is constant here. I'll do cell 1, 2, so it's the same issue here. I need row total, which is 144. So let's start that again. Okay. And use the parentheses again. Row total times column total. In this case, the column total is 279, and divided by this sucker right here. There you go. You know, sometimes you can actually do this dragging function, but it won't work so much in this case because the way the table is set up. So I'll just write these in separately. So let's do for cell 2, 1. So we get equals row total times column total. So this is, in this case, column total is 152 again, right? Divided by grand total. And then let's do the next one, cell 2, 2. So we have row total times column total divided by grand total. Make sure I got this all right. Let's see. So we got here. Sometimes I might mess up somewhere. So this was for, let's just make sure, I want to make sure I just got it right. So this was row total times column total C. Yeah, got that right. Okay. And 2, 2 was 1, 2 row total, right? E9 times, oh, I did that wrong. It should have been D. There you go. That should have been D. There you go. That's better. That's what I was worried because we're all the same. There you go. All right, let's do the next one here. So now we're down to here. So the row total here. Row total is 156. It's this cell. Let's put the parentheses here. This cell times this divided by 431. And then finally the last cell, it's the cell that includes 100. It's equal to 156. So that's row total times the column total divided by 431. Okay, here we go. So now we have our frequencies, our expected frequencies, and we have observed frequencies. To calculate the chi-square, you see the numerator is the difference between the observed and the expected. So I'm going to go ahead and square these first. So, in Excel, you have a bunch of functions pre-made. So if you use them a lot, it'll show you most recently used. If not, you can just look under, like, say, math and trig. So I need a square root. So I'll go under square root somewhere, and I'll find it. There it is. I hit square root, and it says, okay, what is the number? Well, what I need is I need the square root of, I didn't need square root, sorry. But now you know how to do square root. I need the square, actually. Square is power, sorry. But I'm glad I showed you how to do that. Power, here it is. So the power has 2 arguments. I need the number itself. So the number in this case is going to be the difference between the observed and the expected. So it'll be this cell, isn't that cool? C8 minus this guy right here. And the power is 2 because we're squaring it, right? That's your power. And we get that. There you go. The next one, let's see. Let me show you something. If I drag this on, let's see what will happen. What will it do? So it'll probably give me the wrong one here. C9. Yes, we don't want C9. There you go. That's what happens if you drag it. So you got to be really careful if you use that. In this case, we wanted this value here minus this. That's perfect. So now it's okay. Okay. Make sure that's right. So E8, oh, not that, sorry. It's D8 right? D8 minus H6. Yep, there you go. All right. Now let's go ahead and do the next one. So we can just keep on doing this if we want. You can do it however you want it. Now, once we've done it a few times, power will fall under our most recently done functions, and you can just use that. So the number in this case is 44 minus the expected value for cell 2, 1, and we're doing the power. Okay, and then the next one is you need cell D9, right? D9 right here, right? This is our cell 2, 2, right? This is row 1, row 2, column 2. So let's do power again. And we get the difference between this minus this squared. Okay. I love how sometimes these numbers work out so perfectly, don't you? Isn't that great? And then we have find the last two cells. You notice already that these differences are quite small, so that's something that's interesting, right? Let's see. And then we have last two. We get, again, we're going to do power here. So what's the observed for cell 3, 2 minus the expected, 3, 1, excuse me, minus the expected. And then raise that to the second power. And finally, the last one, we'll do cell 3, 2. So let's go power again. Power cell 3, 2 minus the expected frequency. Square this difference. Okay, there you go. So now we're all set. Now we are all set here and ready to go with our numerators. Next step is we need, and I call it the element because this is the element in this equation here, right? It's this quotient here. So now I'm just going to do, in each case, I'm just going to do this quotient. So I'm hitting the equal sign. I'm taking what's in this cell, and I'm dividing it by the expected frequency, which is right here, right? So this is the numerator divided by the expected frequency, which is in the denominator. I hit equal. Now, in this case, I have everything set up. I have I have the expected frequency, and I have the numerator. So everything's going to be exactly the same. It's always going to be what's in J divided by what's in H. So now I can just drag these down and just repeat the same equation. And all it's doing is repeating the equation. To show you that, let's highlight one of these. This is J9 right here. J9 divided by H9. So this is these are my elements, and if I sum these up to sum, I can just hit auto sum and hit enter. And I get 0.23391 as my chi-square value. So in the chi-square analysis, we're looking at expected minus observed distribution. The null hypothesis, that's the hypothesis we'd like to reject, is that there is no difference between the expected and the observed distribution. The alternative is that there is a difference. I calculated, or earlier I told you that our critical value is 5.99. You can get that from a critical value table. This is from my textbook, published by Kendall Hunt, publisher. This is a chi-square table. If what I neglected to say was, in that case, if I select our alpha is a probability of type 1 error. So that's a probability of a false positive result. We always set alpha at the start of research, and generally people like to work with 0.05. A 5% chance of a false positive result is an acceptable level for most people. That's just by convention. It doesn't have to be. If you know about stats, you can just ignore that rule, or the heuristic, I should call it. We had 2 degrees of freedom, right? And with an alpha of 0.05, our critical value was 5.99. So that's why I selected 5.99. And if we look at our calculated value, well, to judge significance, I always tell my students to write down the rule, write down the rule for, it's called decision rule. Let's see, do this here. I'm going to just type that down here. Decision rule. Let's see. Reject the null hypothesis if the calculated value exceeds the critical value. I always say is greater than or equal to. A lot of people don't like it when you're equal to the critical value, but you can just say exceed it. So in this case, if we look at our results here, our calculated value is 0.23391. You don't have to be a genius to know that that's not exceeding 5.99. So in this case, we would fail to reject the null hypothesis. We'd fail to reject the null hypothesis. So therefore, we cannot conclude that there's a relation between education and physical activity. If there was, you'd see a clear difference between the observed and expected values. If you look at these, they're very close, like 44 and 46, 87, 84, 56. I mean, so that is a clear indication that we have nothing there. Well, anyway, I hope you enjoyed this. If you have any questions about how I did this in Excel, please comment, and I'll be happy to answer. Have a good day.